So this is going to be a couple applications of what solving for a system of equations is going to be. We'll get much more in depth later on, but these are just fundamental facts how these are useful, even in just electrical engineering. Okay, so the two major applications we're going to be using are network of flow or network of channels and an electrical flow, because that's the key thing when it comes to solving for system of equations. But network of flow can go through a lot of stuff: water canals, city streets, anything that has a flow of some type of traffic goes through this type of network. So the example of each one. So network flow kind of looks like this. Kind of like that. It's kind of like a flow of traffic, whether each one is like a light or a stop sign, right? So anything that has like that, even water propulsion goes through, right? Or these are like the drain pipes, or cool, interesting stuff. So that's what network channels are. Electrical flow is, if you guys taken any physics before, this is probably going to look very, very similar. I should put one here. So kind of like this, where you have a flow where it's going to be in this case, the intensity going through it. But we'll talk about that later, and the voltage and all that fun stuff. Okay? But these are the major types we're going to be dealing with. Okay? So first off, let's talk about networks. So networks are circles or nodes that are intersections. So these are the intersection nodes, respectively, where it's going to go. And the lines or branches are the streets. Again, right, flow of traffic. The total flow into the node is equal to the total flow out of the node. That's the key thing. Okay. So total flow is equal to two things: the sum of in and out. Okay. So for example, here's one node, and if I have 50 going in, and then I have 3 going out, where let's say this is x1, x2, and this is 20. So therefore, I know just based off what in and out represents. So 20 minus 50 is 30. So 30 is the sum of what's coming out of this node, right? Or the sum of x1 plus x2. Okay, and that's how these processes are going to work. Okay, and this is how we're going to set up our system of equations. And just remembering all flow goes in must come out, right? Or more flow can also go in, but it has to eventually pour out somewhere. Okay, so here's a little example how we're going to do this. So what we want to do is just set up a system of equations that represents traffic flow for this network. Okay, and we'll go a little further than that, but for now we just want to try to set it up. Okay. So we have a bunch of these nodes everywhere, right? We have a bunch of variables everywhere, and we have numbers going in and out of each node individually. And we're just going to use this situation to write a breakdown. Okay. So we're just going to go down each node. We have 6 different nodes. So we'll say node A. So how much flow is going into A is a total of just 800. Right? Everything else is coming out. So we know 800 is equal to the sum of going out. In this case, it's x1 plus x5. And we're just going to go all the way around and do the exact same thing. So flow in for node B will be this, and looks like that's it. Okay. So we have, so this is going in, so we have x1 plus x4 equals everything going out, so 400 plus x2. Okay. Now we go to C. So what's flowing into C is just x2. What's flowing out is x3 plus 600. Now go down to D. What's flowing in is 1600 plus x3. And what's coming out is 400 plus x7. Okay, keep going. Node E. So what's flowing in is only x7, and what's coming out is 4 and 6. And then finally, F. So F has two things coming in, 6 and 5. And what's coming out is 400 plus 600, so we can just put 1,000 there. And there's our representation, or our system of equations. Okay, so now what we want to do is put it into our matrix. Okay, now the problem when it comes in a matrix, we got to be very careful. The first thing we have to do before we do any setup is have all the variables on one side and the numbers on the other side. Okay, meaning like this. So just an 800 here. So basically, I'm going to have to bring this over to keep this by itself. Bring that over. Bring this over to keep only the numbers there. And then for node E, I would actually bring everything over to set it equal to 0. Okay. So when I do that, and I'll show you how to do the nodes themselves. So therefore, if I do node A, B, C, D, E, and F, respectively for each individual equation, well, it'll be x1, x5, right? So I've got to kind of count what's going on here. And it's going to equal 800. And we have a total of 7 letters. So we have x1, x2, x3, x4, x5, x6, x7. Right? So this represents that equation. Okay? And I'm going to follow that same template down. Okay? So just remembering we first have to bring over x2. So this is going to be 1, negative 1 for x2, 0 x3s, 4, 5, 6, 7, and this equals to 400. Okay. And again, we'll follow the same pattern. Bring this over so we have 0 x1s, 1, negative 1, 0, 0, 0, 0, and then 600. Okay. A, B, C, D, A, B, C, D, D down. All right, so D has 0, 0, 1, 0, 0, 0, negative 1. And if I bring this over, actually, you know what? Let me change it up a little bit. Let me make it positive. Oh, it's a positive 1200 here, not negative. Okay. All right, 2 more. We have E now. So this is all going to be, so we have 0, 1, 2, 3, 4, 5, 6, 7. And this is equal to 0. And 1 more down here. And then finally F. 1, 2, 3, 4, 5, 6, 7, 1000. And there we go. Here's our system of equations. Now we could technically solve for this because it's actually not that bad. A lot of this just goes away eventually, but you know, give or take. But eventually, after we do all of this fun work and all that, we get this. There we go. So it looks like 7 and 6 are independent variables, and then 1 through 5 are dependent variables. Okay. And now we can solve for a general, this is our general equation. We can solve for a particular one, just picking anything you want. So like you could pick x to be 100, this to be 200, and eventually you get some processes there. So, kind of nice, right, when it comes to it. Okay. Now, the cool thing is we can now monitor. So like, why is this actually interesting going forward is, well, what if let's say, speaking of traffic, right, we've all seen the streets. What if a street is closed, right? It just blocks. So in other words, flow of traffic isn't going this way anymore. Or these are all one-way streets, right? Like, if you go to LA or San Francisco. So now, what happens if, let's say, we say if x1 equals 0, and so does x2, then what? Okay. What happens to this flow of traffic? So now, if I just represent everything, just rewrite this whole process, but now knowing x1 and x2 are 0, this flow in is 0, and so is that. So it doesn't matter the orientation, it's going to be 0. Okay, so let's see what's happening. So flow in must equal flow out, right, in that portion. So let's go back over here. So if these are 0, somehow things have to balance everything out, right? So now what happens is, from C to D, it was going this direction. But to cancel out in and out respectively, this has to change direction because it's going outwards. So how can things go out when you come from nothing? So this now alters its direction here to that case. Okay. This is still going in because it was a constant fix. This is still going out to a constant fix. This is now going this direction. So let's see what's happening. So it forces a lot of stuff to alternate respectively, right? Now, let's look at B, E to B. So flow in was 800, right? It added out, it was out, that's good. So flow in is 800, this is going out. So what else was it going to, right? So usually, in this case, here, in B, down here, it was going inwards. This is still going inward to get the 800 to balance out the 400. This is now going to 200. Okay. Now the biggest change is this one, right? It was the opposite. Because flow is opposite, this represents x3 actually goes to a negative. It just flips direction. So if I would solve for a system in this format, I would have to change x3 to be a negative because the now flow is in the opposite direction. That way everything correlates to each other, respectively. Okay? So it's pretty interesting when it comes to streak lines and options like that. Okay. Now the other type of one is network. And this one you got a little bit more physics applied to it. Okay, so electrical network. So before we get into it, we need to know a couple things from physics. Okay, so first thing is Ohm's law. So Ohm's law says the voltage drops across a resistor is the product of the current and the resistance. Remember, product means multiplication, so just remember that, right? So current is usually denoted as I, and resistance is usually denoted as R. Okay, so voltage is usually denoted as V. So in other words, V is equal to I times R. Okay. Now, next one is Kirchhoff's first law. The sum of the currents flowing into a node is equal to the sum of the currents flowing out. So kind of like the network, flow in equals flow out, right? When it comes to when you're going into a node. Okay? And the last one is second law. His second law is the algebraic sum of the voltage drops around a closed loop is equal to the total voltage in the loop. So the sum of the voltage drops around a closed loop is equal to the total voltage in the loop. Pretty tricky situation, right? We'll talk about this one. This is the one we're going to be using the most when it comes to voltage drop and the sum equals the total voltage. Okay? So let's try an example out so you can see how this is going to be applied. So we have our loops here, right? Our electrical network. And in fact, we actually have two loops, since we're talking about loops, right? Here. So our first loop, if I just follow the current, so let's say if you didn't want to start here. So I go here, then I have two spots. I can go there or there. So if I go here, in this direction, I go here, I see the resistance, go back to C, and I just follow this format because it doesn't show me I'm going this direction. I have to follow the same format. So it looks like I have one loop here. And then this time, at B, if I go this direction, keep going, and then I follow this process going back up. So it looks like I have two loops. I have loop 1 and loop 2. There. Okay, so that's how we do that portion. But now the question is, how do I use these networking properties and these laws to signify an actual equation? Okay, so now we're going to use second law, but we're going to do loop by loop. Okay, so our first loop, it goes, if we start at B, it goes B. Oh, actually, I need more letters. Sorry, there's something I'm missing here. There you go. D or T. Okay, that's what I was looking for. A, B, C, D. Okay, that's all I need. So we're going to go loop B, D, C, and then B. So we're going to do loop second first. Okay. Now, what does this look like? So if I follow this format. Okay. So now we're going to use the second law to help ourselves out. All right. So this one says the sum of the voltage drops. So we have voltage. So the sum of the voltage is equal to the total voltage. So our total voltage is 10. So what is the sum of these voltage drops? Okay, let's see. So this one goes from here, and then it goes through here, and then comes back. Goes through here, and then comes back around. Now remember, this is going in the opposite direction. So we're going to have the voltage going back to here, right? It says the voltage drops, so V equals I times R, so our resistance is 10. So our current is 3, so it'll be 10 I3. And instead of plus, I'm going in the opposite direction of I2. So it'll be minus, again, the resistance, which is 10 I2. And then we do the same thing for loop 1. So in this one, in loop 1, we're going to again start at B. Now this time go to C, A, then back to B. So this had a voltage of total of 5. Okay. All right, so again, if I follow the same voltage portion, it's going to be 10 I2. And if I follow it, and notice this time it's in the same loop, it's not going in opposite, so it's going to be plus 20 I1. And there is our system of equations we're going to be solving for now. We're just solving for I1, I2, and I3. So we're going to have a 3 by 3. So if I just follow this format, I'll do this one first. We have no I1, so it'll be 0, 10, 10, 10. And this one's going to be 20, 10, 0, 5. Now, we actually have a problem. because we actually haven't used this one. Or have you used one, the Ohm's law and second law, but when do we actually use this one? And this is going to be our third equation we need. Remember, this one says the sum of the currents flowing into a node is equal to the sum of the currents out. Now, B is our only node where currents are going in and out. So at node B, we have total in, which is I1, is equal to total outputs, which is going to be I2 plus I3. So just like when it comes to network, when you have this, set one side, all the variables on one side and equal to a value, and this is going to be 0, so we actually have a next one down. So bringing over I1, or actually, I'll just bring everything else over. So we 1, negative 1, negative 1, and 0. And now we have our system we can solve for. And if you notice, it's actually not that bad to do on hand, but I'll skip that step for now. So after doing some calculations, we get an answer. And the best part is we get an actual unique answer. Okay. So therefore, current 1 is 0.4, current 2 is negative 0.3, and current 3 is 0.7.